Good evening, one and all. Greetings from ChemPlus 2021. This is Priyansh, Secretary, Chemical Engineering Society of IIT Madras. It gives me great pleasure to introduce our guest speaker for the evening, Professor Dr. Rafiqul Gani. Dr. Gani is the co-founder and CEO of the company PSE for Speed, providing innovative, accurate, and consistent engineering solutions very fast to industrial clients. He is currently an adjunct professor at the Korea Advanced Institute of Science and Technology and a visiting professor at Texas A&M University, College Station, USA. Sir shall be delivering on next generation of process system engineering and sustainable chemical engineering in today's lecture. The audience is welcome to post questions on our YouTube live stream, and they will be conveyed to Sir after the lecture. Sir, thank you for being with us today. We can start this session whenever you're ready.
Okay. I hope everybody can see my screen and hear me. So it's a great pleasure for me to give this lecture. I would like to thank Professor Srinivasan, the Secretary of the IITM AICHE student chapter, and all the organizers for making this very nice program. So as the session chair said, I will talk about process systems engineering and its application in chemical engineering related to sustainable processes. The lecture is divided into 5 parts. The first part is where I will introduce the topics and the concepts. So starting with what I would call a multi-layered view of chemical and biochemical engineering, the basic objective in our view of chemical and biochemical engineering is that we take resources and we convert them into products that we need for our sustainable society. And in order to do that, we need the process. We use the chemical and biochemical engineering fundamental principles to design the process, to control the process, to operate the process, and so on. One could ask if this core fundamental is enough. What we would say, it's not enough, because we need to know the demand of the resources, the availability of the resources. We also need to see if the product can be improved and the waste can be reduced. To do this, we need more than the fundamental. We need a combination of science and engineering, which will lead us to then sustainable technology. And then we could ask, is that enough? We would say, well, we need more, because the resources could be location dependent, is type dependent, is recovery dependent, and so on. The product needs to be optimal, the waste needs to be the lowest, environmental impact needs to be controlled, and so on. So to do this, we need integration of ideas, disciplines, data sources, and so on. And that will lead us to the final sustainable development of industry institutions for the society. So in this scheme, what you can see is that in the vertical sense, from bottom to top, we apply the knowledge to get what we need, our objective. And in the horizontal sense, it shows the overall objectives of our principles, that our main contribution or deliverable is the products and the processes. And how do we do that? And what we use is the horizontal. And as we go outside, we are adding more and more information. So what is the chemical and biochemical engineering contribution? We identify the problem, we generate alternatives and also evaluation of them. We develop methods and tools. We do mitigation or management with respect to education and training, influence decision makers, and so on. That's our multi-layered view of chemical engineering. Now let's see what is process systems engineering. Process systems engineering is all about the development of systematic techniques for process development and use for process modeling, design control, and many others. This was the definition that was given in the first Process Systems Engineering Conference in 1982. Our objective is still to convert resources to products, needed products through process. Later in 2004, Professor Sargent gave a more detailed definition as a systems approach, which is some formulate their problem or some useful simplification of it in precise mathematical terms, then seek to exploit the mathematical structure to obtain an effective algorithm, while others seek insight on the problem structure from physical intuition. And we will see how this is actually applied to many of the cases that I will be discussing. Also, we can say that PSE is use of systematic approach to problem solution, also use of computer-aided and systematic approach to solving process engineering problems. What we see is that the scope and significance of PSE or CAPE, computer-aided process engineering, is potentially very large because we can solve not only the chemical and biochemical engineering domain, pharmaceutical, food, life science, energy, biomedical, and many more. What we are doing is contributing to managing the complexity with problem solution. Now with that, we can see an adopted view, multi-layered view of process systems engineering. So instead of the fundamental chemical engineering principles, we have the modeling, synthesis, design, control, numerical methods as needed to get to model the process, design the process, operate the process, analyze the process. And then in the intermediate layer, we combine engineering and science with respect to artificial intelligence, machine learning, model predictive control, process intensification, and so on. And then in the outer layer, basically it is similar as the chemical and biochemical engineering, except that the methods, ideas, disciplines, data sources, integration we are talking about are related to the PSE methods and tools. But the overall objective is the same. So what I will highlight are the fundamental core topics of PSE, which is modeling, synthesis, design, operation, control, planning, scheduling, numerical and computational aspects. Also, I'm going to talk about sustainability and sustainable development. So let me define what sustainability in my view is. Very simply, it is the ability to sustain or the capacity to endure changes to the system. If we look at the plot, on the y-axis is the human progress, on the x-axis is time. The green curve needs to go up as human progress is increasing. But what you see is that other curves, which we can call subsystems, increased and then stopped. So what it means is that subsystems can become unsustainable, but before a subsystem becomes unsustainable, we have to find another subsystem which can take us forward. So because of that, you can see that at different times, periods of our evolution, different subsystems started and became unsustainable, but we continued. And that is, in a very simple way, what we call sustainability. But sustainable development, I like this definition given by the Brundtland report from United Nations in 1989, development that meets the needs and aspirations of the present without compromising the ability of future generations to meet their own needs. It's a very good definition, but the big question mark is, are we actually doing this? And I would say that if we look at many of the actions, not just individual, of countries, of regions, they're not really following that. We can also look at, I think about 10 years ago, United Nations also proposed 17 development goals for sustainable development goals. And if we look at goal number 7, goal number 12, goal number 13. These are very much related to what we can do as chemical engineers and process system engineers. Also, I think these days the curve on the right is very familiar to people with the infections of COVID-19, that the infections are going up and we need to bring the curve down. This is also very true for sustainability. The climate risks, if it is business as usual, will just go up. There is a capacity of Earth, and if we go beyond that capacity, things become unsustainable. So what we have to keep below the limit of Earth's capacity so we can remain sustainable. So with this background, I will go and discuss part 2, which is overview of the core fundamental topics of PSE. And these are on the first column on the left-hand side, the 5 items: numerical analysis, computer science, synthesis, design, optimization, systems, and control theory. All of these are actually related to modeling, or modeling is a subtopic in all of them. So we have not put the modeling as an item separate, but modeling applies everywhere. And so it's a very important thing in process systems engineering. So why do we need, for example, numerical analysis and computer science? We need to perform simulations, data analysis, so numerical analysis is needed. What is the outcome of that? We can understand the system, we can, the behavior of the system. Based on that behavior, we can develop intelligent systems. Synthesis, we can synthesize molecules, materials, process. That would be the outcome by applying the methods for product and process synthesis design, and so on. So I will give more details of that as we go on. So first, modeling. Why do we need modeling? What you see on the left are the systems which we need to study and for which we need to solve the problems which you see on the right. It can be design problem, production problem, planning problem, safety analysis, many more. So we have the system, we have the problem we want to solve. Now, if we have enough knowledge and enough data, we should be able to solve these problems if we have a method to utilize those data and knowledge. So if we have a design method and we have enough data and knowledge, we should be able to solve the problem. But the difficulty is that in most cases, the data available or the knowledge available is not complete. And therefore, we need a model of the system. And then we solve the model equations through simulation. We generate additional data, and this additional data then completes the data needed so that we can solve the problem. So model and the role of model is very important. And most model-based systems contain models, numerical solvers, algorithms. Examples of model-based systems are process synthesis, process simulator, control monitoring system, planning, scheduling, and many more. If we have the models, as we said, we need to solve the equations, so we have numerical issues to address. So here is an example where if you look at the left-hand side, define the problem. Let's say we want to define a simulation problem. We define the problem, we give the flow sheet, we need a model. So we need to provide the model equations, which can be steady state, dynamic, different types. We collect the additional parameters. Then when it comes to solving the model equations, we need a solver. That's the numerical issues. And then we analyze the results. But when it comes to solution of the model, there can also be just solution of the model equation, or not just solving the model equation, but also do the optimization in terms of design or in terms of minimization of profit, cost, or maximization of profit. So we need various types of solvers that need to be connected, from equation solving algebraic equation, differential algebraic equation, partial differential equation solver, and optimization, linear programming, nonlinear programming, mixed integer linear programming, and mixed integer nonlinear programming. All of these, if we have, then we have a complete set of tools through which we can study a wide range of problems. What is the synthesis problem? On the left-hand side, you see different unit operations. If we do the synthesis at the scale of unit operation, the objective is going from left to right. We have some raw materials on the left. We want to produce some products on the right, and we need to find the optimal path, optimal steps, and the technologies to use in the step to get the optimal solution, the path. So for example, this is the path. Once we have found this path, the process design problem comes. For example, in the reactor, what should be the temperature, pressure, reactor volume to give us the conversion that we need? Or the separation, if it is a distillation column, what are the number of stages, feed location, etc., that gives us the separation. So once we do the design, once we get the processing route, then at this point, we can say that we have a feasible design of a process or a base case design. And then we need to evaluate and see, is this the best design or can we improve it? I will talk about those later, but that's the design problem and the synthesis problem. Now the product synthesis is very, very similar to the process synthesis, as I said. If you consider that we have atoms like carbon, hydrogen, oxygen, we combine the atoms to form functional groups, and which can be unit operations. And the functional groups then are combined together to form molecules, which will be the flow sheet. And then these are different examples of compounds. And then if we say that this particular one is an optimal molecule, it is optimal in the sense that we have defined some target properties, and this molecule satisfies those target properties. So that means if we had a flow sheet, we will do the simulation, we will look at the mass balance, energy balance, sustainability, cost. So this is similar to calculating the properties of the compound and checking if they match the target. So product and process synthesis are very similar if we look at it in this form. The control problem, I think, is very common. We have a unit operation that we want to operate at our designed condition, and we want to make sure that if there is a disturbance, the controller is able to bring the system back to the steady state operation. So we need to understand the process. We need to have a model that can duplicate the behavior. We need to add a controller. We need to design the controller, and then we need to find the optimal operation of the process. So given the system, determine the control system design, verify through simulation or experiments. Also, there is a lot of there are lots of processes that operate in the batch mode. For example, we have 3 batch reactors that have 5 modes of operation. What should be the sequence and period of the 5 operations for each reactor so that there is continuous production? That's a planning and scheduling problem. Another interesting non-chemical engineering problem could be finding the sequence for these operations that you see for a washing machine. What should be the least time and the least amount of fresh water needed to get the washing that we need to do. So all these are planning and scheduling kind of problems, and these are very common in pharma, food, cosmetics, aroma industries, also non-chemical engineering applications. The kind of mathematical problem solved, again, represent the problem mathematically and find a way to solve it. You can see all of them are related to this. And the kind of problems we solve are MILP, MINLP. So now I've given you some overall ideas of the kind of processes. What I'm going to show you now is a general mathematical formulation of a wide range of problems. We want to optimize, so we have an objective function. We have design specifications, which is equation 2. What is the purity, for example? We have the process. We need a process model. We have chemicals, so we need a chemical model, property model. We have constraints on the design variables. What should be the temperature? What should be the pressure of the reactor? We have molecular structural constraints, how to make a molecule that is chemically feasible and matches the target properties. And then we have the process network, that is the superstructure I showed you during process synthesis. So this problem includes integer variable, real variable, and it can be as little as 7 equations and as big as 7 million equations. It can be linear, nonlinear, all combinations are possible. The solution method, we can solve it direct. There are many examples, like if we want to do a heat exchanger network, that would be a direct solution. Decomposed, if we want to solve the process synthesis problem together with the design problem, it can be decomposed. Also, it can be hybrid. That means start with the decomposed, then switch to direct solution and get the solution. So there are different solution approaches. So again, you can see we represent the problem mathematically, we analyze the structure, and we find the optimal solution strategy. So here is some examples of how the general problem formulation can solve a wide range of problems. So you see the equations on the left-hand side. And if we are solving only equation 3, it's a process simulation problem. If we are solving only equation 4 and 6, is a product simulation problem, you can say, to verify the product. If we use equations 1, 2, 3, we are doing optimization of the process and so on. Now, I will not go into the details of the optimization strategy, but I will, through a cartoon, like here, I will give you the concept of the optimization. So the idea is that Wally, he's called Wally in English, in Spanish called Waldo, in Danish called Holger. The idea is to find Holger in the picture. And you can think of Holger is our optimal solution. How do we find it? We magnify, magnify, magnify until we find Holger. So which is that? And what we are doing is we define a search space and we continuously reduce the search space until we are able to locate the optimal solution. That actually is also how most of the optimization method works. Okay, so I'm just giving the concept in order to not to go too far in time. So now let's look at some of the PSE methods and associated tools. The process simulator is the most common. I think everybody knows it. But remember that process simulator is not a process engineer. It does not decide. The process engineer decides. Whatever the process engineer gives, the process simulator calculates and gives. A very common problem is the process simulation. You give the flow sheet and you perform the simulation. And on the picture, you see an ammonia process. So given a flow sheet and the design, you can perform simulation. You can do optimization control. If you have a working simulation, you can do process integration if you know the hot streams and cold streams, and also sources and sinks for mass integration. And you can do analysis if you have all the data from the simulation. So this is one of the biggest contributions of process systems engineering, because you can think of that at any time on Earth, somebody is using the process simulator. While this is also a very big contribution, it can also be a little bit negative, and we can see it from here. So we want to do process we know that we can use the simulator for process simulation. but only if we have the flow sheet. So how do we get the flow sheet? Or if we want to optimize, how do we know that the design is the best? Or if we want to control, how do we know which is the control? Or if we want to know that is the process safe? So the way we do it now, because we have the simulator, is that we start with a trial solution. We evaluate our objective. If the objectives are not satisfied, we put a new trial and we continue. So we have an inner loop with the simulator and an outer loop to check our objective. That's a trial and error solution. That cannot be a very efficient way to do it. So while we have the simulator that allows us to solve problems, but it is not actually helping us to solve efficiently. And doing like this, it is almost impossible to find novel or innovative solutions. So what we see is that we need some extra things. The extra things could be, if we need a new solvent, can we find a new solvent, a new compound, a new model, a new process flow sheet, new hybrid unit operations? How do we find them? We need methods and tools for them linked to the simulators. So we can think of that we have a library of databases with all kinds of data. We have library of models, not just at the unit operation level, at various levels. We have synthesis and design methods, not just for the unit operation process synthesis design, but also molecular design, process synthesis at a lower scale, intensification, hybrid separation, and so on. And then if we have all of these and we are able to find a solution, we can always go to the simulator to check. And then once we have simulated, we can do the analysis, not just cost, but also with respect to sustainability, life cycle, and many more. So what we see is that within this structure, simulator is just one of many tools. And this is an advertisement of our company. We have a collection of tools for ProCAPD is for product design, then property prediction, flowsheet design, refrigeration design, and then MOT is a modeling tool. SustainPro is to calculate the sustainability, and so on. All of these are linked to commercial simulators. So whenever one wants to do the simulation, it can. So it complements the use of the simulator rather than competes with them. I will skip the modeling part here. And then what I want to highlight is, how do we solve the problem? Almost every day, new products and processes are coming, and people are mainly using experiments. So they have a system under study, they do experiments, and when they reach a solution they like, that is their solution. That is what I would call reality. If we replace it with computer-aided tools, I would call it virtual reality. We have a model of the system. We do virtual experiments. We get a final solution. And now the question is, we have a solution from reality. We have a solution from virtual reality, which is the best. In both cases, we cannot guarantee optimal solution. But if we have experiments, we can verify our model-based solution through experiment. The model-based solution can give us innovative, novel solutions if the model of the system that we are using is predictive. That is, it can extrapolate outside the system data. Only then we can give the predictive. So again, modeling is very important. And then we can see that we can integrate the reality with virtual reality. The data from the reality can be used to develop the model. The virtual experiments can guide the design of experiments in reality, and we can cross-check the solutions in both. And after that, we need to do the final analysis with respect to sustainability, environmental impact, and so on. So what is needed is actually an integrated approach, not just model-based, not just experiment-based, but an integrated approach. With that, I will give you some examples. And before I go to the examples, I want to highlight that our main purpose is to convert resources to products, and what you see on the boundary on the right-hand side are the different products we need for sustainable development of society. But what we see is that in the current state of the art, if we continue like this, we will not become sustainable, we will become unsustainable, because we are close to hitting the Earth's capacity in terms of changes. So we need to improve our process significantly. Improve with respect to waste, improve with respect to energy, improve with respect to efficiency, everything. So some of the methods I will discuss are related to that. But first, let's see the challenge facing us. We humans on Earth are the master, but what should we do to remain at the top? We need to handle the challenge of water, food, energy, environment, and the relationship between them. So that is what I will show, how we can address that, and at the same time find sustainable solution. Why is this a problem? If we look at the growth of population on Earth, it is increasing. Maybe it will come to 10.5 billion by 2050. What does it mean? The food demand will increase. These are according to data and extrapolated. The water demand will increase. The energy consumption will increase. And all of this will increase the CO2 emission, or GHG. And what does this mean? It means that with such growth of population, the GDP has to increase, the production capacity with respect to cosmetics and other things, consumable things, need to increase. That will increase the energy demand, the electricity demand, the water demand, and will increase the emissions. So what does it mean again? This is again data. The Earth's temperature is increasing, and we need to do something to decrease that. And what is the consequence of that? These are real pictures, not produced pictures, but real pictures, and this is what has happened. So we need urgent action, slow down the global warming, reduce the water land contamination, stop the forestry destruction, recover and reuse resources, and many more. So how do we do that? Let's take the first case. Here is a typical example, the HDA process to make benzene from toluene and hydrogen is very well known. The flow sheet you see is a well-known flow sheet. But is this the best flow sheet? What we can do is we can take this flow sheet and generate other alternatives. We can see that we can generate 64 other alternatives that nobody has checked. Now, which alternative is the best? We do the very quick simulation. So we need a model at a lower scale so that without doing mass energy balance, we can find out what is the carbon footprint and so on. And then we can choose a flow sheet that has the best, most promising factors, and we calculate all the analysis, and we find out that this flow sheet is actually 25% better than the original. That's a significant improvement. That's what we are talking about, that we need to have significant improvement compared to the current one. Another thing we can say is that if we want to achieve significant improvement, and also in the short term, what are the possibilities? So I'm going to show you another example that process intensification provides a very good opportunity. What you see on the left are different chemical processes. Most chemical processes have reactor followed by separation. Can we combine all of this into one reactive distillation, which again will improve all the criteria for comparison by at least 25%. The following questions on the right-hand side, if the answer is yes to all of them, we can easily find what should be the non-reactive section, what should be the reactive section, what should be the non-reactive section at the top and bottom, condenser and reboiler, and we have a reactive distillation that will replace the entire process into this. That's a significant improvement. And this can be done short term because now I would say reactive distillation is already a known technology. Also, we need to reduce energy. Most chemical processes, a large percentage of the energy is for vapor-liquid separation. And if we take an example of where the vapor-liquid separation takes a lot of energy, this is a process, deethanizer, depropanizer, demethanizer, like that. And we do the simulation and we find that the shaded columns use a lot of energy. So what can we do? These are distillation columns. We have a long-term solution that we can replace the distillation totally with a membrane, but we need to find the membrane that can replace totally. On the other hand, we have a short-term solution where we do not need to change anything in the distillation, but we put a small membrane unit where the permeate is not the light compound, which normally would be, but the impurity. So the more impurity we remove, the more pure the product becomes. And this is a very small operation of the membrane, and together they can be a very good combination. The rule for these combinations is that combine two types of techniques such that each operate at its highest efficiency. Alone, they cannot reach this efficiency, but when you combine them, the combined efficiency is good, and it is possible to save between 10 to 50% of the energy of the single column. Now think of that if there are 100,000 estimated operating distillation columns on Earth, how much energy could be saved on the short term. Now, all of these things that we have said, we can say that the process is here, and this process releases CO2, and we reduce this CO2 to zero. Does it help us? What I would say is that it does not help us because we also need to look at the energy that would be needed to run the process. And so the power plant that provides the energy will emit CO2. So we need to put the boundary in the right place so that both are taken into account. And then we need to see where is the energy coming from. If it is fossil fuel, it will release CO2. If it is other sources of energy, it may not release so much CO2. So we need to look for a combination that will combine the energy demanding technology like our process with the energy supplying technology like the power plant in such a way that the net CO2 is zero or negative. If we can achieve that, then we can solve this kind of, we can contribute to the global warming, reduction of the global warming. And this can be looked at in a more detailed way. Here is the process and the synthesis of the process. We are assuming that whatever power we need is available, whatever water we need is available. But if we put a limit, then that would be the limit. And then if we say this energy and water will come from different sources and they can be obtained from different ways, then we have different networks. And then again, the objective would be to find a combination that will give us zero or negative CO2 emission. That's network within network within network optimization. If we can do that, if we have the models and the techniques to solve them. This is already solved for a problem that we published in last year. The last example is chemical substitution. We are using chemicals everywhere. These chemicals have harmful effect, and we need to be sure that before a chemical with a harmful effect is released, we identify it and we replace it with something that is not harmful. And that's a very, very big problem. And if you think of, at this moment, there are nearly 1 million chemicals that are being used in all kinds of products. And nearly 90% of them have some harmful effect if they're used beyond a threshold limit. So they need to be identified and they need to be replaced with another that does not have the harmful effect. A very simple example is, let's say benzene is a very good solvent, but is carcinogenic, and so it has a harmful effect. Can we replace benzene with something else? So we define the problem, we define the search space in terms of what kind of molecules we want, the size of molecules, then we define the target, that is the properties, and then we combine the atoms to groups and the groups to molecules and find how many molecules satisfy our targets and satisfy the constraint that they will not be carcinogenic. And here is one example of that. Similarly, we can do integrated design and control. Because of the time, I will skip this. What I will say, something to think about, is that we should not take for granted that whatever solution we get is good and accurate. We need to confirm that the solution is actually correct. Also, if we look at the future of which techniques would be, computer-aided techniques would be important, modeling and simulation is very high, big data is very high, cloud computing, automatic learning, these are very high. So these are also some things to talk about in terms of where we should focus in terms of development of methods. So finally, perspective and conclusions. I will go very fast in here. So we have the challenges that I mentioned: water, energy, food, health, resources, and their relationship on Earth. This is the challenge, but finding solutions is the opportunity. So as I've shown you some examples, those were the opportunities we have to tackle these problems. Another one is that we want to achieve, let's say, sustainable development or circular economy. What are the measures in terms of resources, in terms of service, in terms of products? How we can replace the resource, we can replace a service, we can improve a service, we can increase the time horizon of availability, and so on. The means, PSE techniques, unification of methods and tools, integration of engineering and science, core PSE topics, fundamentals, and then the research that is needed. So I'm going a little bit fast in here. Then we can say that, as you have seen, we need a number of methods and tools and ideas. All of these need to be integrated together to solve the problem. And 4 examples are here, that we want to find novel materials that can be catalysts, membranes, adsorbents. And then we need to combine with the fundamental simulation, optimization, control, design, synthesis. If it is the effective healthcare, it's the same with respect to vaccines and pandemics. If it is smart manufacturing, it is the same. So in every case, PSE provides the glue to integrate the different methods and tools and data for solution of a wide range of problems. And then I will end with this problem that we have been actually working with, and it's a good opportunity for all of us. We have the planet Earth. The system characteristics is that it can be Earth, it can be continent, country, state, city, whatever. Then within the country, let's say, what is the number of regions within which the country can be divided? Then within each region, how many people are there? Within each number of people, how many groups of people we can say? And then we could say that how many vaccines do we have available, and how should we distribute the vaccine so that the number of people dying within a certain period is the minimum. So that's a very nice optimization problem. We, in addition to the vaccine allocation that I've explained, we can also have discovery of the vaccine or the drug, sustainable manufacturing of the drug or vaccine, distribution and delivery, that is planning and scheduling of that. And the final one is plan and implement the vaccine allocation, giving of the vaccine. So optimal distribution so that the death is minimum. And then again, you need knowledge and data, models, mathematical representation, solution strategy, solvers. That means we manage this complexity. With that, I want to end by listing out the role of chemical engineers. Chemical engineering and related sciences and technologies must play a key role in meeting future societal demands. We should promote research and development as a fundamental pillar and encourage technology development to achieve a planet able to sustain a growing population while improving quality of life. That's the Sustainable Development Goals. Facilitate global dissemination of chemical engineering technical knowledge and so on. Promote conservation and care of global resources. This is very important, health, safety, environment. Promote the highest standards and professional ethics and conducts. And finally, prepare for the next pandemic or disaster with methods and tools that can contribute to quick problem resolution. With this, I finish my talk and I'm open to questions. Thank you very much.
Thank you very much for the very informative session, sir. We have a few questions here from our audience. So the one question goes, does the industry practice the methods you mentioned in the lecture, and which ones would require more research?
Well, I would say that I have close contact with industry, and many of the things that I've mentioned is being solved by the industry that with whom I'm working with. Of course, it's not widely distributed over all kinds of industries. The most common of all kinds of industries is actually process simulation and process optimization, and maybe also in some form properties prediction. But dissemination of the latest results to the industry is more on a, I would say, personal contact point of view rather than general dissemination from academia to industry. So we have to do much better.
Thank you, sir. The next question goes, even if we find a solution for chemical substitution, what about the chemicals already put in the environment in the past years of development?
Yes, this is also what I meant by prevention is better than cure. That if we have not looked at the analysis of the chemical and released the chemical, we have already caused the pollution. And then addressing that problem is much more difficult and costly than preventing it from the beginning. So yes, there is a lot of chemicals that are around. I mean, CO2 is there, of course, but water has a lot of other chemicals that, and land has a lot of other chemicals. And those pollution problems is expensive to address. And so we as engineers have to look at not only curing the problem, but preventing the similar problems in future. That's why the methods need to have, solution need to have an analysis of environmental impact, of sustainability of these things so that we can avoid these problems in future.
Thank you, sir. Another question goes, although process intensification is very promising, but for the countries which are mostly based on SMSEs, how are we making technologies more cost effective?
Yes, this actually process intensification has a lot of promise, but unfortunately, when it comes to application, also related to the first question, is difficult to find where actually it has been applied. And there are two reasons. One is that some companies they have applied the process intensification. They have very good solution, but it's confidential. And some others, they don't have the means to do the spend the initial amount of money that needs to be spent to implement the intensified solution. There is also a third option, let's say problem that we have seen is that even though we provided an intensified solution, the company had a guarantee from the supplier of the technology. And if they changed anything in that process, the guarantee would be lost. So there are some practical issues that also need to be sorted out. So that is probably, these are probably the reasons why finding or implementing the solutions that seem to be very, very good is not yet being applied. And also what has been shown in recent research, it is not even a problem also from a control point of view, from an operational point of view. The reactive distillation or dividing wall column with non-reactive reaction can operate and can be controlled very well. So there are no difficulties in operating. It's just the initial incentive of the companies to invest on this solution and see what can be achieved. That initial breakthrough is difficult to achieve. But from my private connection with some of the companies, they have developed pilot plant, and I would guess that the next step would be that they will expand from the pilot plant. So it depends on the company whether they're interested to do it or not. But the potential is there.
Thank you, sir. Next question goes, can systems someday learn of new parameters by themselves analyzing error distribution?
Can you repeat it? I couldn't understand.
So can systems someday learn of new parameters by themselves analyzing error distribution?
Yes, this is what data analytics experts and machine learning and AI people would say, that in principle it is possible, but more work is needed to guarantee that. What I can see is that definitely using data and model, much better model can be developed now through machine learning than before. So because much better correlation of the data and interpretation of the data can be obtained through data analytics and machine learning methods. But there's also a negative thing, whereas example model, and I'm talking about this from property prediction. Toxicity is a very difficult property to predict by all kinds of methods. And those models that are available need only 10 parameters. Whereas a machine learning, which actually does the model very well and matches almost all the data, very high accuracy, needs maybe 10 times more parameters. So, of course, if you have more parameters, you can model the system much better. And here, machine learning AI methods are helping us who cannot get so many parameters or understand how so many parameters will interact. They're able to figure out how to do that. So at least in these steps, it is going in the right direction, but more work needs to be done. I hope I've answered the question.
Yes, sir, definitely. Thank you very much, sir. One last question is from a master's freshie. So she asks which companies are currently working on sustainable development, and from a freshie's point of view, can we think of making a career in this field?
What was the second part?
From a freshie's point of view, can we think of making a career in this field?
I didn't understand the word. Sorry.
From a fresher's point of view,
I
can we
see.
think of making a career in the field?
Can we think of what?
Making a career in this field.
Making a career. Of course, I would say that all big companies, multinational companies, I don't know about the Indian companies, but let's say multinational, whether it is BASF or whether it is ExxonMobil or whether it is Dow Chemicals, if you check, or pharmaceutical companies like Pfizer, AstraZeneca, all these companies in their objectives is sustainable development and sustainability and life cycle assessment. So these are among the top criteria that they have. And all of them also are working on CO2 mitigation and so on. So these are, and the question is how one would do it, achieve it. So there one can say, okay, we can replace distillation with membrane. So there's a lot of research on membrane, but how long will it take before we can get a membrane to replace distillation? And should we wait until that, or should we find more short-term solutions? So these areas are very good. And what process systems engineering and chemical engineering provides is that one is trained to solve not just one problem, many problems, whether it's pharmaceutical or petroleum engineering or bioprocess or food. The model is different. Interpretation of the variables are different, but the solution strategy and the solvers are the same. So if one is trained to understand and develop models and use model-based systems in a systematic way, they can apply this to all kinds of engineering domains. So one does not need to be fixed on one area. It can be a wide range of areas. So I would say that look for the systems approach and the systematic ways to solve the problem. And if you're interested in data and model and equations, for me, it's the same. In some cases, it's database modeling. In some cases, it's mechanistic modeling or a combination of both. So, and then if you're able to represent your system with data and models, and then you can see how many different kinds of problems you can solve and which of them have significance. So that again, and that's why I showed the challenge, is that it is important to solve problems of significance rather than trivial problems. But if you have this background, I don't think you will have any problem of becoming an expert or finding a job in related fields.
Thank you, sir. With that, I would like to close this session. On behalf of the entire organizing committee of ChemPlus 2021, I would like to thank you, sir, for sparing your invaluable time, joining us, and making this a memorable evening. We hope to stay in touch with you and invite you in our future events as well. Thank you again, sir.
Thank you very much, and I wish you all the best, and also take care. The pandemic has not yet finished, but we need to do the last step before we are ready to go back to normal. So take care, and I wish you all the best in your studies and in your future career. Thank you.